Okay, so now we'll look at what is called a bridge edge and how to use the result of depth first search to decide whether an edge is a bridge edge or not. Now, an articulation point, if you remember, is for a vertex. So if we remove the vertex, whether the graph gets disconnected or not. Now, in a similar comparison, we can say a bridge edge is with regard to an edge. If I remove the edge, whether the graph gets disconnected or not. So if the graph gets disconnected, then we can call the edge as a bridge edge, otherwise not. So for example, in this graph here, if I remove this edge 0, 3, the graph will get disconnected with 0, 1, 2 as one component and 3 and 4 as another component. Similarly, if I remove the edge 3, 4, 4 is going to be isolated from the rest of the vertices. On the other hand, if I remove this edge 0, 2, all the vertices are still going to stay connected. Okay. So similarly, if I remove 0, 1 or 1, 2, all the vertices are going to still stay connected. So we can call 0, 3 and 3, 4 as bridge edges, whereas the other 3 edges are not bridge edges. So given a graph, how to decide whether an edge is a bridge edge or not? So the general rule is this. So let us pick up an edge UV and we want to decide whether UV is a bridge edge or not. So now what we need to first decide is between U and V, which is kind of what is called an ancestor, or we can call upstream, no ancestor, upstream node, and which node is called a downstream node. So we need to decide that first. So between U and V, which is an upstream node and which is a downstream node. So an upstream node is the one that is more closer to the root of the depth first search tree. Okay, so let us say in this, I have not shown here the depth first search tree involving U and V, but assume that U is more closer to the root of the depth first search tree. So U is the upstream node and V is the downstream node. So what we now need to look at is the subtree rooted at that downstream node, which is including V and anything further down. So the rule is this: from this subtree, including this downstream node, there should not be any back edge coming out of that going to either U or above U. Okay. So that means all back edges associated with the subtree should originate and end within that subtree. If there is any back edge that comes out of the subtree going to U or above U, then this edge UV is not a bridge edge. For a simple reason, if say there's a back edge that comes out of the subtree and goes say either to U or anything above U, which is indicated with this circle here, then removing UV is not going to cut off any of the vertices. The graph is still going to stay connected because this back edge will be connecting the vertices of the subtree to everybody else. On the other hand, let us say there is no back edge that comes out of the subtree. Then if I remove this edge UV, the subtree vertices are going to get disconnected from the rest of the vertices. So that's the rule. So you should not confuse this with articulation point. So remember, for articulation point, from the subtree there could be a back edge that goes up to U. Now only if it does not go beyond U or above U, then we can call that U as an articulation point. So even if there's a back edge that comes out of the subtree that goes only up to U but not beyond U, then U could be called an articulation point. Whereas for a bridge, there should not be any back edge that goes even up to that U. Okay, so that's the difference. Alright, so let us apply this rule here. So we'll run depth first search on this graph. So let us say start from vertex 0, so push vertex 0 to stack, then go to vertex 2 and then push it. So that's the second vertex we push to a stack, that's a tree edge. Then go to vertex 2, that's also a tree edge. And then back up, so we cannot go further down, so this is a back edge. and pop out 2 from the stack, and then pop out 1 from the stack, then come back to 0. We cannot pop it out yet because there's another neighbor not yet visited. So go to 3, that's the fourth vertex we pushed, tree edge, and then go further down to vertex 4, that's the tree edge, that's the vertex number 5 to be pushed, and then go, cannot do anything else. So fourth is the vertex 4 is the fifth vertex we pushed to a stack, cannot go anywhere else, so pop out 4 is the third vertex we popped out of the stack, and then back to 3, cannot do anywhere else, go, so pop out 4 from this vertex 3 from the stack, that's the fourth vertex we popped out of the stack. Now back to vertex 0 on the top of the stack, we cannot go anywhere else from vertex 5, so that is popped out, so that's the fifth vertex to be popped out of the stack. Okay. Now this is the depth first search tree, starting from 0. So now look at this edge 3, 4 that we won't classify as a bridge edge or not. So 3 is the upstream node because it's more closer to the root, and 4 is the downstream node, and there's a subtree involving 4, but there's no back edge coming out of the subtree. So 3, 4 is a bridge edge. Similarly, 0, 3 is a bridge edge with 0 as the upstream node, 3, 4 is a subtree with 3 as a downstream node. Now there's no back edge coming out of that subtree. Whereas in this case, say 1, 2, 1 is the upstream node, 2 is the downstream node, and there's a back edge that goes above 1. Now 0, 1, 1 is the downstream node, 0 is the upstream node, so there's now a subtree with 1 and 2, and there's a back edge that goes up to 0. So because of this, 0, 1 and 1, 2 are not bridge edges. Now back edges are definitely not going to be bridge edges, because if you remove them, the graph is still going to stay connected. So the rule is this: back edges are not bridge edges, so only tree edges are candidates for being considered as bridge edges. Okay, so this is another example for bridge edge. We did this depth first search earlier, but let's do it quickly. So start from vertex 1, push vertex 1 to the stack, and go to vertex 2, that's the tree edge. So push 2 to the stack, go to vertex 4, push vertex 4 to the stack, third vertex we pushed. Now from 4 you can go to 3, fourth vertex we pushed. From 3 to 5, that's the fifth vertex we pushed. Then 5 to 6, sixth vertex we pushed. So those are tree edges. Then from 6 you try to go further down, you cannot go anywhere. It is a new vertex. We have back edge to 4. So pop out 6 as the first vertex we popped out. Back to 5. You have back edge to 4. So I cannot go anywhere else. So pop out 5 as the second vertex we popped out. Back to 3, cannot go anywhere else. You have back edge to 1. That's it. You cannot go anywhere else. A new vertex. So pop out 3, that's the third vertex to be popped out. Back to 4, cannot go anywhere else, so that's the fourth vertex to be popped out. Back to 2, from 2 you can go to 7, that's the seventh vertex we push to a stack. From 7 you have back edge to 1, cannot go anywhere else, so you have to pop out 7, so that is the fifth vertex to be popped out of the stack. And then back to 2, and from 2 you can't go anywhere else, so that's the sixth vertex to be popped out. From 2 now back to 1, nowhere else you can go, that's the seventh vertex to be popped out of the stack. So if you put together the results of the tree edge and back edges, so this is the depth first search tree, and now the back edges are not bridge edges. Now for the tree edges, 2, 7, you see this is a subtree involving 7, and 2 is closer to the root, so that's the upstream node, and 7 is the downstream node. Now from this subtree there is a back edge that goes above 2, so that's not a bridge edge. Now 1, 2, you have 2 as the downstream node, 1 as the upstream node, and from this subtree with 2 and everything further down, there's one back edge, actually 2 back edges that go to 1. So it should not go even to the upstream vertex. So all back edges should start and end within the subtrees if at all they are present. So in this case there are two back edges that go up to the upstream vertex. So 1, 2 is not a bridge edge. Similarly 2, 4, there is one subtree and there is one back edge that goes above 2. So no bridge edges in this graph, or there are no bridge edges in this graph. Okay. So I stop with this.